Welcome back to the Deep Dive, the shortcut to becoming truly well-informed. Today, we are really tearing into the foundation of the modern enterprise. Cloud infrastructure planning.
That's right.
Technology is no longer just a supporting component of the business.
Not at all.
It is the engine of competitive differentiation, driving smarter products and generating entirely new revenue streams.
Yeah, digital transformation is fundamentally about accelerating that whole business life cycle. And, well, to achieve that competitive speed, you need a flawless technical blueprint. So this deep dive is really essential for anyone who needs to understand the nuts and bolts of how modern, scalable IT is built, not just the buzzwords.
Exactly. And we're focusing on two foundational lessons that, form the bedrock of any successful deployment.
The core stuff.
First, the design goals. That's kind of the North Star, the why, and then the comprehensive design process, the rigorous methodology that dictates the how.
Right. Our mission today is to quickly distill those key principles that really differentiate successful cloud design from, well, the old way of doing things, traditional static infrastructure planning. We want to move past just general concepts and focus on the concrete steps, the trade-offs you have to make to engineer systems that are truly elastic, functional, and secure.
And right out of the gate, we need to flag something critical you mentioned from the source material. Designing for the cloud is fundamentally different from building a traditional data center.
Absolutely fundamental.
So what specifically is the aha moment here? What really differentiates this modern approach?
I think the biggest mindset shift, the real aha, is around availability.
Availability? How so?
Well, we're used to thinking that availability resides solely in the underlying physical infrastructure, redundant switches, dual power feeds, mirrored facilities.
Making the hardware bulletproof.
Exactly. But in the cloud, that responsibility shifts dramatically. It moves increasingly up the stack, and it's handled more and more by the application layer itself.
Okay, so the application has to be smarter.
Precisely. We're designing applications now that expect failure and can recover instantly, rather than designing infrastructure that tries to prevent every single failure. And that changes everything about the design process we're about to explore.
Okay, let's unpack this then. Before an architect even thinks about drawing a diagram or picking a vendor, they need to establish these high-level guiding requirements. These are our design goals, and they aren't technical specs yet, are they? They're more like strategic mandates.
That's a great way to put it. Design goals represent the desired end result. They are the high level, the sort of general requirements that act as the consistent guide throughout the entire design process, which can be quite long and complex.
Right.
They essentially tell the architect where the organization wants to go, in terms of capability, cost, agility.
And that crucial distinction you mentioned earlier, cloud versus traditional design, that seems absolutely paramount here.
It is.
If we miss that foundational difference, we're basically just building a virtualized data center on someone else's hardware, not a true cloud platform.
You've hit the nail on the head. Traditional infrastructure planning focuses almost entirely on mitigating physical component failure, making sure the hardware doesn't break.
Right.
Cloud computing, though, alters the very methodology of how services are deployed and scaled. It's a different game.
So if the design process keeps focusing only on preventing hardware downtime,
it completely misses the boat. It misses the potential for cloud-native scalability, for agility. The application layer itself, it has to be designed differently, maybe stateless, resilient, allowing for that horizontal scale-out and rapid deployment that, frankly, traditional monolithic designs just can't handle. That inherent resiliency built into the app is what truly delivers availability in the modern cloud sense.
Okay, so if the whole availability model is shifting upwards, what are the core characteristics that a successful cloud infrastructure design must deliver after it's built? This is like the architect's final exam checklist.
Yeah, it really is. The source material lists 5 core characteristics. These are the fundamental goals for the resulting cloud infrastructure.
Okay.
1. Elastic. The ability to scale resources up or down dynamically quickly based on actual demand.
It's a classic cloud promise.
2. Available. Ensuring the system meets the defined uptime, the recovery objectives, but with that application layer resilience baked right in.
Got it.
3. Secure. Protecting data, protecting systems through comprehensive controls that understand things like multi-tenancy and distributed architecture.
Non-negotiable.
4. Supportable? This one's key. Ensuring the system can actually be maintained, monitored, operated effectively over its entire lifespan.
Okay, we'll come back to that one.
And 5, functional, meaning it actually achieves the purpose, the business objectives it was designed for in the first place.
Right. We understand elasticity and availability. Those are, like you said, classic cloud selling points. Security is obvious, but let's zoom in on supportable and functional, because sometimes these feel like they get glossed over in the rush to deploy something new. Why are they so crucial as high-level goals?
Well, think about supportable. If a system isn't supportable, it quickly becomes a massive operational sinkhole. It just eats up time and resources, completely destroying any cost benefit you thought you were getting from the cloud.
Right. The TCO goes through the roof.
Exactly. Being supportable means the organization has clearly defined operational procedures, they have comprehensive runbooks, robust monitoring and logging that's integrated into some kind of standardized platform, and critically, that the configuration is documented and traceable.
Traceable. That sounds important.
It is. It links directly back to the need for clear standards documentation, which we'll definitely talk more about later. If you can't easily trace what's happening, monitor it effectively, and quickly fix problems when they arise, then it's not really a cloud-ready system, is it? It's just fragile.
Okay, that makes sense. And functional. That connects the tech back to the actual business reason we're doing this.
Precisely. It's not enough for the VMs to spin up quickly or the network to be fast. The functional goal ensures that the final deployed product actually delivers on the strategic vision that was laid out in those initial goal statements.
So if the goal was, say, faster feature delivery to beat competitors.
Right. But the resulting infrastructure is so complex and slow to provision that developers hate using it. Well, then it failed the functionality test. It doesn't matter how technically stable it is. These goals offer that broad direction. They're the starting point for gathering all the granular requirements later on.
Okay, let's make this more tangible. Can you give us some examples of what good high-level goal statements might actually sound like? Remembering, these should focus on business value, not the tech itself.
Sure. Think about statements an executive or a business leader might provide. Something like, we would like to provide our developers the ability to provision infrastructure on demand. See, that's a goal. Focus squarely on agility, developer empowerment. It points towards self-service capabilities.
Okay, clear business outcome.
Or maybe, we wish to reduce the data center footprint by 60% within 24 months. That's a very clear, measurable, strategic goal.
What?
Probably driven by cost savings, real estate efficiency.
Yeah.
Or maybe something broader, like, we would like to offer all of our customers the ability to use our application in a secure and cost-effective manner. This one cleverly combines that security imperative with the business need for low operational expenditure for efficiency.
Got it. So these goals are really the why. They give the architect that crucial understanding of the organization's strategic destination before they even start mapping out the technical journey.
Exactly. You need the destination before you draw the map. So goals give us the destination, but the path, how we get there, that's defined by the process. And what's really fascinating here, I think, is that cloud infrastructure design is defined as an entire process. It's a structured methodology, not just, drawing a diagram and handing over a parts list.
Right.
This standardization, this methodical approach is kind of the secret sauce for getting consistent, reliable results, especially in large organizations.
So we're talking about moving away from maybe ad hoc projects, things driven purely by individual heroic efforts, and moving toward a more repeatable, almost industrial approach to building cloud platforms. What defines this methodology we need to use?
Well, the process mandates using a standardized methodology. The whole point is to ensure consistent deliverables across different projects, different teams. And this standard approach, it's vital because it helps manage risk. It helps avoid those painfully prolonged development times. It ensures you actually capture all the business needs up front. And frankly, it provides a much more professional front to stakeholders. They see a plan.
Makes sense.
Yeah.
Now, let's clarify the distinction between a framework and a methodology, because that word rigidity seems important here for our audience.
Good point. A framework is generally a more loosely defined structure. It's a set of guidelines, maybe.
Like an outline.
Kind of. It might outline the overall goal, maybe the high-level steps needed to get a result. Think of it as maybe a conceptual map of the territory you need to cover.
Okay. So conversely, a methodology is much more specific, like turn-by-turn directions.
Exactly. A methodology is a more rigid set of actions, processes, rules. It defines how to accomplish a specific task. The steps have to be reproducible, standardized, so you can get a predictable end result time after time. For instance, TOGF, the Open Group Architecture Framework, that's a well-known open framework. But it includes a detailed methodology that can be applied across all sorts of enterprise architecture projects, including cloud.
And that rigor prevents critical steps from being skipped, maybe? Like validating requirements?
Precisely. It forces a discipline that you might not get with a looser framework.
Okay. Given that rigor, defining the scope and the boundaries early on must be absolutely critical. Got to prevent that dreaded scope creep.
Oh, essential. Absolutely essential. The architect has to define the scope right up front. You have to clearly state what the design includes, and maybe just as importantly, what it excludes.
Good point. What's not in scope?
Yeah. For example, the architect might state, okay, this design includes defining the compute, network, and storage requirements for the new private cloud platform. But it explicitly excludes the design of a brand new data center facility to house it, or say the organizational change management required to get people to actually use the new cloud.
Right. Setting expectations.
Exactly. It delineates responsibilities, manages stakeholder expectations, and keeps the project focused and hopefully manageable.
And as this design process moves forward, the deliverables, the things the architect actually produces, they need to cover both logical and physical design considerations.
Yeah.
Right?
Yes, they do.
What does that mean practically?
So the infrastructure design has to provide both kinds of blueprints. The logical design addresses the abstract stuff, the relationships between components, how data flows, security zones, the overall architecture. It's the what and the why.
Okay.
Then the physical design, that specifies the actual hardware configuration, where things go physically, connectivity details, rack space, power needs, maybe even specific vendor models. That's the where and the how it all plugs in.
Got it. Logical is the concept, physical is the concrete implementation.
You got it. And you need both to actually hand off to an implementation team to build it.
Now, this whole process, it sounds like a deeply collaborative effort. It's not just one person in a room drawing diagrams.
Not at all.
Which brings us to what might be the most crucial soft skill for any architect: communication.
Oh, absolutely. Communication is the absolute lifeblood of this design process. It has to be effective, it has to be frequent, and it involves talking to everyone, stakeholders, business users, and especially those subject matter experts, the SMEs.
The people who know how things really work.
Exactly. The architect's job isn't just drawing diagrams. It involves a surprising amount of diplomacy, actually.
I can imagine.
The key communication duties include knowing how to ask the right questions, the clarifying questions, being able to explain really complex technical reasoning behind decisions in a way people understand, sometimes educating stakeholders on new terminology, especially with cloud, and constantly reviewing design decisions to get that validation, to get acceptance along the way.
Yeah, I can picture a scenario where maybe the business wants some super expensive cutting-edge feature, but the budget constraint is tight. The architect needs to clearly communicate why. Based on those constraints, they have to go with a simpler, maybe less flashy, but more practical alternative.
Exactly. That scenario happens all the time. And the final crucial step in this communication duty is actually defending the solution.
Defending it.
Yes. At the end, you have to be prepared to stand up, present your final architecture, justify every major decision you made based on those requirements, constraints, and assumptions you documented, and answer, potentially pointed questions from skeptical parties.
Sounds intense.
It can be. But this whole communication cycle, it's iterative. It runs right from that initial assessment phase all the way through the final sign-off. Constant communication.
Okay, here's where it gets really interesting, I think. We move from those high-level strategic goals into what sounds like a forensic investigation. You need this to build a truly functional blueprint.
Forensic is a good word for it sometimes.
So the cloud solutions design project lifecycle, it typically breaks down into three main phases, right? Phase 1, understand requirements. Phase 2, plan and design.
Yep.
And Phase 3, implementation and validation.
That's the typical flow.
Let's dive deep into Phase 1 now, because this seems foundational. It's all about accurate data gathering and making sure you've understood correctly.
Yeah, Phase 1 is absolutely about establishing the baseline reality. It kicks off with a really in-depth assessment of the organization, its existing assets, its operational landscape, especially as it relates to the project at hand.
Okay.
We're clarifying goals, yes. But most importantly, we are nailing down the three critical elements that define the entire design envelope: requirements, constraints, and assumptions.
Right, those three again.
Without that granular understanding of the existing environment, the current hardware software configs, the real pain points people are experiencing, the actual operational and business objectives, well, you're basically designing in a vacuum. It won't work.
So before we can even start thinking about, I don't know, which specific cloud services or hardware we might use, we need to gather just a massive amount of detail. What are the key focus areas we should be looking at when gathering requirements?
The scope here is pretty expensive. It goes way beyond just simple CPU counts or memory needs. We have to gather detailed requirements in areas like, first, quality attributes, those non-functional requirements or NFRs, things like security posture, specific availability targets, performance benchmarks.
Okay, how well it needs to work.
Exactly. Then operational integration. How is this new platform going to integrate with existing monitoring tools, existing self-service portals, current automation workflows?
Critical for supportability later.
Absolutely. Then service definition. Defining things like multi-tenancy rules if it's a shared platform, what types of services go in the service catalog, maybe even how billing or chargeback will work.
Right, the operational mechanics.
And finally, business and compliance. Reviewing the existing business processes that this platform will support and ensuring any strict compliance needs, regulatory industry standards like HIA or PCI, are met from the ground up.
Okay, that's comprehensive. Let's really focus on distinguishing between those three key guiding factors that come out of all this data collection: requirements, constraints, and assumptions. Getting these right seems like where an architect really proves their value.
It really is. So requirements are the must-haves.
The non-negotiables.
Pretty much. These are the functionalities or characteristics that must be included in the design for it to meet the overall business goals. And importantly, they have to be actionable, measurable, and testable.
Testable is key.
Crucial, for example, the system must process 1,000 transactions per second, or customer data must be encrypted at rest. If you can't test whether you met the requirement, it wasn't a well-defined requirement to begin with.
Okay. And then we hit the constraints. If requirements define what we have to build, constraints define the box we have to build it inside.
That's a perfect analogy. Constraints are those conditions or items that inherently limit your design choices. They often come from outside forces you can't easily change.
Like budget.
Budget is the classic one. But also tight project timeframes, maybe physical space limitations if you're doing a hybrid model, existing corporate policies, technical debt from old system, all sorts of things.
Right.
Identifying those constraints really early prevents the architect from, designing a beautiful $5 million solution when the budget is only $1 million.
Okay. But what happens if a requirement, a must-have, directly conflicts with a constraint, a limitation? How does the architect bridge that gap? Is that where assumptions come in?
Assumptions play a role here, yes. Assumptions are basically expectations that you use when you don't have solid requirements or concrete data.
Filling in the blanks.
Kind of. Maybe the current storage utilization trends are completely unknown because monitoring was bad. So the architect assumes a 20% annual growth rate based on industry averages. This lets the design move forward. But these assumptions must be documented clearly and crucially reviewed immediately with stakeholders to get agreement.
Validation is key.
Absolutely. An unvalidated assumption is just a risk. It's a potential design flaw waiting to happen if that assumption turns out to be wrong.
And speaking of risk, what's the critical technical homework regarding how systems interact that needs to happen in this phase? You mentioned dependencies earlier.
Yes, you absolutely must identify and document all the dependencies. These are the other technologies, or maybe even business processes, that your new solution relies on to function correctly.
Okay. Examples.
Sure. If your shiny new multi-tenant application relies on the company's existing, maybe slightly creaky Active Directory for authentication, or it depends on a specific third-party SaaS provider for critical logging services, well, those dependencies introduce potential single points of failure. They introduce limitations that have to be factored into your design's availability model, its security model. You ignore dependencies at your peril.
Got it. So how do we actually get all this information? It sounds like a mix of digging through technical data and talking to actual humans.
It really requires a two-pronged attack. First, you need the technical data collection.
The objective stuff.
Right. We use specialized tools, discovery tools, monitoring tools to gather the hard metrics. Real-time data, historical data on resource usage, allocation patterns, performance statistics of the existing infrastructure. This gives us the unbiased picture of how things are actually being used and where the current bottlenecks or pain points might be.
But the server utilization stats won't tell you about the organization's political landscape or maybe historical grudges against certain vendors.
No, they won't. That requires the human factor.
Talking to people.
Exactly. This involves interviewing the key stakeholders, the business owners, the SMEs we mentioned earlier, and this phase demands clarification. You have to keep asking follow-up questions until all the ambiguity is gone. And crucially, once you think you've collected a comprehensive list of requirements, constraints, dependencies, you must formally review them with the organization. Get acceptance, get approval before you move into the actual design phase.
Prevents that awful, wait, we didn't actually mean that moment later on.
Precisely. Saves a lot of pain and rework.
Okay, so once all that raw data is collected, hopefully validated, we move into requirements analysis. This is where the architect starts translating all those needs and wants into measurable specifications.
Yes, exactly. The solution architects take all that collected data and they start analyzing it, typically classifying requirements into functional requirements, FRS, and non-functional requirements, NFRs.
FRs and NFRs.
Okay.
Functional requirements, FRS. Describe what the system actually does. You know, user logs in, process payments, store customer data.
The features.
Pretty much. Non-functional requirements, NFRs, describe the quality attributes. How fast is the page load? How secure is the data? How long does it run without interruption? How easy is it to maintain?
Often called that, yes. And NFRs, while sometimes harder to measure than FRs, are absolutely critical because they define those quality goals, the resilience goals, the supportability goals we talked about earlier.
And this analysis leads directly into managing the inevitable trade-offs, using something called business value analysis, or BVA.
Right. BVA is essentially the formal process for that trade-off analysis.
Yeah.
The requirements analysis combined with BVA, it's often an iterative back-and-forth process.
Okay.
This is where we systematically assess the cost versus the capability for different options. For example, maybe a requirement came in for 100% availability, zero downtime.
The holy grail.
Which is usually technically possible, but financially astronomical, right?
Yeah.
So the budget constraint makes that impossible. BVA helps you determine the most appropriate achievable solution by mapping the actual business value gained against the cost and the feasibility of meeting that requirement fully.
So BVA forces that prioritization.
Exactly. You use BVA to figure out if a requirement is an absolute unshakable must-have, or if it's more of a nice-to-have, especially when you're staring down a hard budget constraint or a tight deadline. All right, so if phase 1 was all about understanding the landscape, collecting the ingredients, mapping the territory, phase 2 is where we actually draw the detailed map, select the vehicles, maybe even set the speed limits. This is the real heart of architecting the solution.
Okay, architecting time. The process here starts by what? Reconfirming those initial design goals we set way back.
Yes, always good to touch base with those North Stars again. Make sure everyone's still aligned.
And then it moves into defining the specifics. What are the core technical components that have to be designed in detail here?
Phase 2 focuses very heavily on defining both the logical and the physical requirements for the key building blocks. Compute, network, and storage needed to actually build the cloud environment.
The fundamentals.
Right. And the architect has to run through a pretty comprehensive technology evaluation checklist. This involves looking at, ideally, vendor-neutral options first, thinking about capabilities, and then mapping those to specific products or services.
Okay, let's break down that checklist. The first point sounds really fundamental, evaluating the build options.
Yeah.
Like do-it-yourself, DIY, versus grabbing a pre-integrated solution like converged infrastructure, CI, or maybe hyper-converged infrastructure, HCI. That choice feels like it has massive downstream consequences.
Oh, it's a huge foundational choice, absolutely. A DIY approach, building it all yourself from components. Well, it offers maximum flexibility. You can pick best-of-breed everything, maybe lower upfront licensing costs sometimes. But it demands a really highly skilled internal team to integrate and manage it all. It significantly increases complexity and the ongoing management overhead. A company might choose DIY if, say, avoiding vendor lock-in is a major political constraint for them.
Okay. What about CI, converged infrastructure?
CI bundles compute, storage, and networking, often from specific vendors, into a single, pre-tested, optimized package. This definitely simplifies acquisition, deployment, and ongoing support because you have one throat to choke, essentially.
Right.
But you do sacrifice some of that DIY flexibility. You're buying into a specific vendor's vision more heavily.
And HCI.
Hyper-converged.
HCI takes it even further. It collapses storage and compute functionality right into the same server layer using software-defined storage. It offers potentially tremendous scale-out capability, really simplified management, and it's often ideal for highly virtualized, very elastic environments like VDI or private clouds.
So the architect has to weigh these options.
Against all those requirements gathered in Phase 1, security needs, complexity tolerance, the organization's actual support capabilities, cost constraints, which option fits best?
Okay. Second item on the checklist, defining the needed cloud service models, IaaS, PaaS, right, is the primary goal to offer infrastructure as a service, IDPA. That means the design needs to focus heavily on virtual machine provisioning, network templating, maybe storage tiers, or is it more about platform as a service, PaaS? Then the design needs to specify how underlying services like databases, message queues, container orchestration will be set up, managed, and made easily accessible to developers.
Got it.
The final architecture must clearly state which service models are supported and how resources will be allocated and managed for each.
And the third and fourth points on that checklist really acknowledge the reality of today's cloud world. It's rarely just one thing, is it? It's hybrid, it's multi-cloud, and you need something to manage it all.
Exactly. The design absolutely has to determine the optimal strategy for potentially adopting hybrid or multi-cloud approaches. How will we securely access external public cloud services when they satisfy specific requirements? Maybe there's a specialized AI service only available on AWS or a data analytics platform on Azure we need to leverage.
Right, integrating external services.
Yeah. And crucially, hand in hand with that, the architect must evaluate and select the right cloud management platform, the CMP.
Orchestration layer.
Precisely. The CMP is that control plane, the software layer that allows the organization to deliver self-service capabilities to users, monitor utilization across everything, automate deployments, enforce policies, whether it's purely on-premises, purely public, or, more likely, some hybrid combination. Choosing the right CMP is critical for actually realizing the benefits of cloud.
Okay. Now, as the architect is putting all these complex pieces together, compute, network, storage, service models, CMP, maybe hybrid connections, we inevitably run into that wall. The reality of design constraints.
It always happens.
We established in Phase 1 what those limits are: budget, time, skills. How does the architect handle that collision between a must-have requirement and, say, an immovable budget constraint?
Yeah, that is pretty much the daily reality of infrastructure design work. The architect will encounter constraints, budget, politics, maybe unforeseen technical limitations. Something will prevent them from fully meeting every single requirement exactly as written.
So what do? Just make a decision?
No, that's the key. They can't operate in a vacuum when this happens. You must involve the stakeholders back in the process. Explain the bottleneck, explain the trade-off options, let them have a say in the design decisions or the changes needed.
Oh, shared ownership of the compromise.
Exactly. It prevents finger-pointing later when maybe a feature isn't quite as fast as originally hoped because the budget forced a compromise on storage performance.
So if we can't meet everything, the constraint forces us to pull out that BVA work, that prioritization from Phase 1.
That's the mechanism. Mitigation requires robust prioritization based on business value. The BVA should have already helped establish what are the absolute must-haves, let's call them Tier 1 requirements, and what are the nice-to-haves, the Tier 2s. So if budget constraints force a painful trade-off, you compromise on a Tier 2 requirement first. You protect the critical business needs, maybe security, compliance, core application functionality, ensuring those are met, even if it means sacrificing some secondary performance goal or a less critical integration capability.
Okay, that makes sense. Navigate the constraints, negotiate the trade-offs using BVA, finalize the tech selections. What are the formal deliverables that come out of Phase 2? This feels like where the paper trail becomes almost more important than the hardware itself.
In many ways, it is. The primary outcome of Phase 2 is comprehensive documentation, not just the technology choices.
Right.
This documentation essentially acts as the contract for what will be built, and it becomes the operational manual for the organization afterward.
Right.
Key documents always include the detailed logical design diagrams and descriptions, the physical design specs, the bill of materials, or BOM, that lists every single hardware and software component needed, and critically detailed operational procedures for actually running and maintaining the environment day to day.
And specifically for cloud environments, which are so dynamic, so defined by software configuration, You mentioned we need extensive standards documentation, too.
Oh, this is absolutely non-negotiable if you ever want to achieve that supportable goal we talked about earlier. Cloud designs must include detailed standards documentation.
Like what specifically?
Well, definitions for cloud internals. How is the self-service portal structured? What specific services are offered in the service catalog? And what are their SLAs?
Right.
And some things seemingly mundane but crucial where many systems fall apart. Naming conventions.
Yes. VM, prod, web server 001 versus web server gem.
Exactly. A rigorous documented standard for naming conventions for hosts, for VM instances, for storage pools, network segments. Everything is foundational for effective automation. Consistent naming allows automated scripts to reliably identify resources, manage them, maybe even remediate issues automatically. And finally, you need standards defining multi-tenancy rules, user roles, capabilities within the platform, and how those map to actual users or groups. That's crucial for security and governance in any shared environment.
Wow.
These documents, they can be massive, very detailed, but they represent the final technical deliverable of the design phase.
And the culmination of all this intense work, all this documentation, is the final presentation, the point where the architect has to stand up and defend those decisions and hopefully get the official sign-off.
Yes, that presentation serves as the formal handover. It's the moment where the architect demonstrates, look, this chosen solution adheres to the requirements we all agreed on, it manages within the known constraints, it rests on assumptions you validated, and here's why it's the right path forward. It's about achieving that final acceptance from the stakeholders and the teams who will actually build and operate it. Hashtag tag outro.
Wow. This has been an incredibly rigorous deep dive into really the essential scaffolding of modern IP infrastructure. We started way up high with those strategic goals mandating things like elasticity, security, supportability.
The North Stars.
And we saw how the design process then meticulously moves down through requirements gathering, finding the measurable must-haves, through negotiating constraints, dealing with the hard limits, all the way to the final detailed documented solution.
Yeah, and I think the synthesis is pretty clear. Successful cloud design requires a real shift. It's moving away from just a hardware-centric break-fix maintenance mindset towards a much more process-centric, communication-intensive methodology. And that need for rigorous prioritization, using things like business value analysis, ensures that when resources inevitably get tight, we make conscious choices. We sacrifice the nice-to-haves, but we protect those critical business requirements that actually define success.
And it reinforces that point you made right at the start, designing the systems and especially the applications running on them to handle failure gracefully. Rather than relying solely on the underlying platform trying to prevent every possible failure, that availability shift.
That's the core mindset change, absolutely.
That iterative nature you mentioned, particularly back in phase 1, where requirements analysis and BVA are described as ongoing back-and-forth activities. That seems like a key differentiator between maybe rigid, old-school IT design and this more agile cloud design approach.
It absolutely is. It has to be iterative because things change, understanding evolves, and this actually leads us nicely into our final provocative thought for you, the listener.
Okay, let's hear it.
So since we know this design process is inherently iterative, and we know that external dependencies have to be identified early and tracked, what happens when a critical new dependency emerges after the formal design documentation is supposedly complete? Yeah. For example, maybe there's an unexpected mandatory regulatory change announced mid-project. Or the company suddenly acquires a key upstream SaaS vendor, changing that integration point entirely. How does the architect effectively use the already documented constraints and the BVA logic from phase 1 to force a rational, cost-effective reevaluation of the must-have requirement list without completely derailing the entire project timeline?
That's a tough one. How do you adapt midstream without chaos? A great question to ponder indeed. Knowing the rigor of this process, understanding these phases is definitely your competitive edge. Thank you for joining us for this deep dive.
Our pleasure.
We really encourage you to take this structured thinking, this methodology, and apply it to your next infrastructure project.